Okay, a little bit more discussion here about molecular orbitals. And let me point out specifically the issue that I particularly want to describe to make sure you've had at least a taste of molecular orbital theory. I mentioned the structure here that we developed for a hydrogen molecular orbital is called a sigma bond, and that's the distinction that I want to make. There are two types of bonds we can think about occurring from the molecular orbital overlap of s and p orbitals. So a sigma bond, and the symbol again is the lowercase Greek sigma, is a bond where the overlap is along the internuclear axis. So internuclear is between the nuclei of the atoms. Axis, right? Like we see there in hydrogen. So if the orbitals directly overlap between the atoms, we can make a sigma bond. There is, however, another type of bond, which is called a pi bond, and that's the symbol lowercase pi for this bond. And pi bonds have the overlap of the atomic orbitals to make the molecular orbital, above and below the internuclear axis. So this gives these bonds a little bit different mechanism of formation, right? And it results in some differences in properties, and that's one of the reasons to understand, at least to a little bit, why this is the case. So in our Lewis structures, if we added a double bond or a triple bond, we didn't think about how that bond was forming. We don't really have a lot of information about how that bond is different from maybe the first bond that we formed, but molecular orbital theory does help describe that. So let's think about these four orbitals we have for bonding in terms of carbon. Right? We've got the s orbital, the 2s, which is spherical. So if we think about forming a carbon-carbon bond, so we've got a carbon and another carbon, right? If we overlap those two s orbitals, they should be about the same size there, we will get a sigma bonding interaction, just like we saw for hydrogen. So these two orbitals could overlap, right, and produce, right, something like that. There's a bonding orbital, it's a sigma bonding type orbital, there's overlap between the atoms, right? And we'd also get the corresponding antibonding type of orbital, which, right, if it's a stable molecule, the antibonding orbitals will not be filled with electrons. Okay. Some of the p orbitals, right, one of the p orbitals anyway, would also be oriented along the axis between these carbons. So if, for example, we looked at this p orbital that is oriented along the axis where we're bringing the carbons together, right? And the sign of this one over here would vary depending on whether we're considering adding or subtracting these orbitals. So I have it here so that there'll be net overlap when we add. We bring these two orbitals together. We are also going to get overlap along the internuclear axis, so that will also be a sigma bond. So this was a sigma overlap. This one will also give us a sigma overlap. So there's the nuclei of the carbons. That would be right in the middle here. The two lobes there that are coming together would combine, so we'd get kind of a bigger lobe of possible electron density there, right? And then the other areas would still be there. So that would be a molecular orbital between these two carbons. That would also be sigma, right? So this would also be a sigma bond. Okay. Now, the other p orbitals are where we get the potential for other types of bonds. Now, you can't really make a molecule with just two carbons. So these carbons would have to be attached to something else. So these two types of sigma bonds, basically we could use one to form the bond between the carbons, but then the other one would maybe be interacting with the other atoms. So we can only make one sigma bond between the two carbons, right? But each carbon could have another sigma bond on the other side as a result of the molecular orbitals. But where the second bond and potentially the third bond and a triple bond come from are the interactions of the other p orbitals. So Again, if we bring two carbons together, but we think about this p orbital, the one that would be perpendicular to the axis of the bonds, right? But easy to draw in the plane here for us. There's another one that's perpendicular that would be in and out of the plane, which is a little harder to draw. If we start to bring these two orbitals together, we're not going to get overlap in between the nuclei, but we are going to get interaction of the orbitals and overlap of the atomic orbitals above and below the plane of the nuclei. So we bring those two carbon nuclei close enough together so that they're bonded. The two kind of open lobes up here will combine, and the two kind of hashed lobes down here will also combine, and we'll get a molecular orbital that looks like that. Overlap above and below the internuclear axis. That's what I described as a pi bond. So this is not a sigma bond, this would be a pi bond, right? And that's how we make the second bond between two carbons in a molecule that has a carbon-carbon double bond. You can make one by a sigma overlap of available molecular orbitals. You make another by the overlap of p orbitals to make a pi bond, right? The other set of p orbitals is the set that is kind of in and out of the plane of the paper here. So one lobe is kind of coming out at us, the other one is kind of hidden in the back. If these two come together, we get a similar situation, right? It's just rotated 90 degrees. The overlap in front of the bond, these two would overlap in front of the bond, those two would overlap behind the bond. We can make another pi bond this way. So this could be the second bond and the third bond in a compound with a carbon-carbon triple bond. So you can make one carbon-carbon pi bond, which would be a double bond because you'd already have a sigma bond, or you can make two, which would be a triple bond. You have a sigma bond and two pi bonds representing the second and the third bond in the molecule. Okay, I think that is a good enough introduction to molecular orbital theory, right? And again, I think not having a note outline is the right way to approach this, because all you really need to think about here are these shapes, right? And how do these shapes interact with each other? That's where all of the pictorial representations of bonding are coming from, is just in your mind overlapping two shapes. You can do that in a constructive fashion where you're adding them together, or a destructive fashion where you're subtracting them from each other, and generate molecular orbitals, right? And you end up with a description of orbitals that expand across entire molecules. So again, if you come back and take organic chemistry someday, you'll get a much more in-depth version of how this creates bonds, how this affects molecular structure and properties, and that is used an awful lot in organic chemistry. Okay, that is the end of chapter 9. So that is the end of new material for Chem 151. There will be videos on practice test 3 coming in the future, and I'll do a video. I don't actually have a practice final exam, but I do have an additional set of problems to get you ready for the final exam in addition to the ones we'll do in lab. I'll try to make videos on those problems as well. So there will kind of be a review set in addition to the one we do in lab of videos for the final exam. So stay tuned for those.